Okay, now let's talk about qubitization. So we talked about quantum signal processing. This was the, I told you that this is a precursor to the qubitization. And the physical model was the always on magnetic field in one direction plus some instantaneous pulses. Okay, and so I told you about this unitary encoding. Which I said that it's of this form. And of course, implicitly, I'm assuming that the norm of this thing is less than. More explicitly, the unitary form, this unitary encoding is actually written here. So there's some notations here. So let me first tell you what these things are. So first of all, I would like to draw an analogy between the quantum signal processing, which was the sequence of our operators that we studied, to the qubitization. And here the z tildes are pretty much the same. It's just the same single qubit z rotations. But now we're no longer working in a single qubit Hilbert space. We're working in a Hilbert space in which we have a single qubit and a quantum system that we want to simulate. The Hilbert space where H acts on. And so naturally you have a tensor product structure. And on the we're going to simply denote the qubit as A. And we say it's A because it's a ancilla qubit, the extra qubit that helps our job. And first thing to notice is that U of H is actually a unitary operator. So how do you see that? Again, like the tricks that I used in previous lectures, you just square it. And if you square it, ZA square is just identity on A. And you have H square. And if you have XA square, that's again an identity. So IA tensor I minus H square. And then you have the cross terms. And that'll be a anti-commutator ZAH and XA identity minus H square. Okay. The first term is obviously just the identity because these two terms they add up to identity. Maybe I'll just be more explicit and say identity on A times identity. The second one, notice that H and square root of I minus H square commutes. So maybe some people are not familiar with this notation. So what this means is very simple. So suppose you have an eigenvalue decomposition of the Hamiltonian, where lambda is an eigenvalue. Then square root of I minus H square is simply this operator. Okay. And because they share the same eigenstates, clearly they commute with each other because they can be simultaneously diagonalized. So this turns out to be actually equal to ZA anti-commutator XA H square root of I minus H square. But of course, this is 0 because Pauli operators, they anti-commute with each other. So we see that first of all, U of H is actually an identity, squared becomes an identity operator. And moreover, we can actually study the block diagonal form of this unitary operator by feeding in explicit states. So for instance, let me make a little extra page here. So suppose we apply U of H to state of this form, where psi is an arbitrary state. And then, well, we have that, and we have this term. And yeah, actually, it'll be slightly more convenient if we, actually, never mind. I think it's still okay to do this. Yeah, so if you do that, then you get 0a tensor h psi plus 1a tensor this thing. And if you apply the same operator to this state, then using the same technique, you get minus 1a tensor h psi plus 0a tensor square root of I minus h squared psi. So if we use the basis of this form, then we can see that u of h can be written down in the following block diagonal form. So here you have h, and here in this in the bottom right block you have minus h, and in the off diagonal entries you have square root of I minus h squared. And the convention would be, let's see, so this will be corresponding to 0 psi, 1 psi for general state psi, 0 psi, and 1 psi. So this is the unitary encoding. Any questions so far?
The determinant of this unitary seems to be -1, not 1, but maybe that's not a big deal.
Let's see. Yeah, I think it's minus, let's see. So I think it is,
Yeah, I'm basically treating h as some number, then.
I'm thinking maybe it's a, well, okay. So first of all, I think it's not going to matter for our purpose, but also I think this might depend on the dimension, because it's not, I mean, for example, like if you have a determinant of minus I in 2 dimension, then that's 1, but in 3 dimension, it's -1.
Okay.
Yeah, so yeah, but it's not going to matter for our purpose.
Yep.
Okay, so as I said, this is called as a unitary encoding of h, and so of course, it's very natural to ask, like, given a Hamiltonian, how can you actually construct this unitary? I mean, after all, we're going to use this unitary all the time. So this is a very valid question. But in this lecture, I will not discuss this issue. But I will give you a hint. And the hint is that you can do that by using the select and prepare operations that I've told you before. Not the select and prepare used for the Taylor series expansion method, but the select and prepare for the Hamiltonian. Okay, so I will stop here for the first part, and maybe, yeah, I think this is a good place to start and have a break. Then yeah, I can take questions.
Yeah, just out of curiosity, this unitary encoding idea, that's
Mhm,
of course very simple. I mean, one could even teach this in quantum mechanics,
mhm.
but this was invented in the context this was invented recently in the context of quantum computation, or was it known long time ago?
Um, let's see. Some people might have known it, but I don't know where this appeared before these works started appearing.
Hmm. So this really started showing up in the context of the qubitization scheme.
Um, to the best of my knowledge, yes, but it could have appeared elsewhere. Yeah, I don't know.
Okay, so if there's no further question, we will come back in just a few minutes, maybe 3-minute break.
Yes.
Thank you.
Okay.
Okay, I guess we can start whenever you're ready.
Okay. All right. So why qubitization? Why is this called as qubitization? It's best to understand this by um, understanding the behavior of this operator to an energy eigenstate of this Hamiltonian H. So, well, let me first slight update of notation. So I'm going to denote this extra single qubit as A and the space that the Hamiltonian acts on as S. S corresponds to system. Okay, and I will consider an energy eigenstate lambda so that H lambda is equal to lambda times the eigenstate corresponding to lambda. All right, so what would happen to this? Let's consider the simplest case. Let's say we have angle, we have this single qubit rotation and U of H, and we have single qubit rotation Z. The question is, if we add this operator on the energy eigenstate, what happens? Well, first thing first, notice that this operator, Z tilde, it does not act on this system register. So we can just commute that out. Okay, and then now we see that U of H has a very nice form. Which is exactly this. This is nice because if we apply H, or square root of I minus H squared to lambda, what we end up getting is a single number because lambda is the eigenstate of these operators. And that just gives you ZA lambda plus XA square root of 1 minus lambda squared lambda S. And at this point, notice that this is just an operator that acts on the single qubit, A. And so it just acts trivially. I mean, at this point, it just acts trivially on this state lambda. And we can say the same thing about this operator. It's just an operator on a single qubit. So it just acts trivially on lambda. So we can pull out all the operators all the way to the right. Get lambda S I psi 0 prime Z tilde ZA lambda plus XA square root of lambda 1 minus lambda squared. And you can see that this argument can be repeated. What I mean by that is consider this slightly more non-trivial case. And imagine applying the this operator to the lambda eigenstate. Then, well, okay, so these angles have changed, but psi 0 changed to phi 0 changed to phi 1 and phi 1 changed to phi 2. But you can still apply the same logic to this thing. And to get lambda S, and well, and then what is this thing? Yeah, you get e to the I 0 phi 0 prime phi prime Z tilde ZA lambda plus XA square root of 1 minus lambda squared. You get that. And again, you apply this U of H to the energy eigenstate lambda, and then what you're going to get is, well, surprise, surprise, ZA lambda plus XA square root of 1 minus lambda squared. So, oh, okay, so sorry. That was just removed. Okay, yeah. So you can imagine if you repeat this many times, let's say n times, you're going to get a sequence of operators. Well, okay, so actually one last thing. So of course you can pull this lambda all the way to the left again. So you can get that thing, and then and the thing is, if you look at this thing, it's a very complicated looking expression, but the important thing is all of these operators acts on the single qubit A, okay? So what we've seen is that if you apply this complicated looking operator, this operator down here, to a particular eigenstate lambda, then you get this like a sequence of effective single qubit operations. Okay. So if you have a general eigenstate, like alpha lambda, general state, which is a linear combination of these things, then you'll simply get this state will be transformed under this operator as sum over lambda, alpha lambda, this thing. You have e to the I psi 0 prime z tilde r lambda, which I'll define shortly, all the way to that, where r lambda is this simple operator. So, and one thing that I will soon show you is that this r lambda is actually a unitary single qubit operator. So once you fix the energy eigenstate lambda, essentially the problem that you have at your hand is just a single qubit problem. And okay, so it's not like I asked the authors what the origin of the qubitization name was, but I get the feeling that this is one of the reasons. So you started with this this problem of synthesizing a unit time evolution operator from this unitary encoding of the Hamiltonian, and what you end up getting is that in the particular energy for each energy eigenstate, you have a sequence of single qubit rotations. And the cool thing here is that this angle lambda, this fixed operation, so that depends on the energy lambda. Okay. So, are there any questions so far?
Yeah, okay. So the results are really wonderful, but it relies on the fact that you are applying this very specific kind of a sequence of operators, E of, single qubit times U of H times single qubit, and so on. What's the meaning of that, of those sequence of operators? Is that the time evolution, or is it, what is it?
Yeah, good. So I will soon show that R of lambda is actually a unitary operator. So you can still think of this as a unit, as a time evolution of a qubit. And but the way I like to think about this is the following. So once you accept that this entire thing is a time evolution of a qubit, okay, so it's kind of a spoiler, but we'll soon show that this entire sequence actually looks like the sequence that we've seen in the quantum signal processing. And there we had a very flexible framework for generating any polynomial P and Q subject to some constraints. And that's where the power comes from. So we can essentially generate a polynomial transformation of H at our will by using this method.
What do you mean by polynomial transformation of H?
Yeah, so maybe yeah, it's better if I go to the next slide. Yeah. Okay. Well, let me just say, well, yeah, I guess we'll talk about that in a few slides. But for now, I would like to compare the sequence of operators that we've seen in qubitization and the sequence of operators that we've seen in quantum signal processing. So in the quantum signal processing, well, so now we remove this A subscript because we're now focusing on a single qubit. In the quantum signal processing, you have this fixed signal, which is e to the I theta x, and you have a variable signal, which is e to the I phi 0 z, e to the I phi 1 z, etc. And R of lambda is of this form, and e to the I theta x is of this form, and clearly they're not exactly the same. So the question is, can we actually relate the two? And I will show you that they can be. So how does this work? So there are some basic things that are that I think I should just tell you. So we've talked about these Pauli operators. There are certain special operators called Clifford operators, which will come in very handy. So Clifford operators, these are unitary operators generated by, this is a unitary group generated by these two elements. This is called as the phase gate. This is called as the Hadamard gate. And for our purpose, we only consider this operator. And the goal, well, okay, so let's first consider some properties of this phase operators. Well, first thing first, if you square them, it's 1, 0, 0, 1 minus 0 minus 1, and therefore it's if you square it, it becomes z. And if you take this fourth power, then it becomes an identity. And Clifford gates are defined in the following way. So Clifford, the gates in the Clifford group are the groups, are the unitaries U, such that U, P, U dagger, or P is a Pauli, is possibly another Pauli. So indeed, S is an element of the Clifford group because if we compute this thing, we get which is equal to y. And if we apply this to y, then you get minus x. Well, I guess maybe I should have saying up to a phase. And if you have applied this to Z, then both are diagonal gates, so they commute with each other. So this just becomes Z. Okay, and the trick here is to basically consider the following operator. So let's try to sandwich R lambda by this phase operator. Okay. In that case, we get this thing. Well, first of all, lambda, we get SZS plus square root of 1 minus x squared, lambda squared, SXS. And S and Z, they all commute with each other. So we can commute S and Z, and S squared is Z. So we get lambda Z squared, and Z squared is identity. So you get that thing. What about the other thing? Get square root of 1 minus S lambda squared, and you get SX S dagger S S. So the point is this is an identity. And that's, of course, equal to lambda I plus square root of 1 minus lambda squared. And this was Y times S squared. But S squared was equal to Z. And therefore, this is lambda I plus square root of 1 minus lambda squared YZ. This is lambda I plus I square root of 1 minus lambda squared X. Okay, so I will just put these things side by side. So S R lambda S is equal to this expression. And what is it? E to the I theta X, which appeared in quantum signal processing, was I cosine theta plus I sine theta X. So now they actually look very similar, right? And indeed, you can choose cosine theta to be lambda to identify the two. And of course, there's this extra gate, S gate, but the thing is, S is actually up to a global phase. The exponential, you can basically generate it by a Z rotation. It's pretty intuitive because, well, S is a diagonal gate and Z is a diagonal matrix, a diagonal 2x2 matrix. So it's, yeah, totally possible. And you can check it. So, yeah, so let's maybe let's be a little bit more explicit there. So you just simply have that. Okay, so therefore, R of lambda, we realize is e to the minus this thing times e to the I x cosine minus lambda, inverse cosine lambda, e to the minus this thing. And that is an important result. Because if we copy and paste this thing, and let's see, go to this next page, and put these side by side, we realize that if we plug in this formula here and here, you simply have terms like this. So you simply get this thing. da da da, and then e to the I x cosine minus lambda, e to the I phi d minus pi over 4. Okay. So of course, we changed the angles, but remember the angle was a variable anyway. So what we've shown is that these sequence of operators that appears in the qubitization upon fixing the energy eigenstate is in fact precisely the same as the let's see, the sequence of operators that appears in the quantum signal processing. Okay, and this was an important realization that really that allowed us to use the mathematics of quantum signal processing for Hamiltonian simulation. Okay. Are there any questions so far?
It's pretty astounding how this all these mathematical manipulations go through.
Mm-hmm, mm-hmm. Yeah. My impression is that they first thought about this qubit problem and then realized that you could extend it very substantially.
Yeah, it's pretty brilliant.
Okay, so if there are no other questions, I'll just continue. Anyway, so you can sort of guess where I'm trying to go to. So we already established this very nice fact. So if you have the sequence of single qubit unitaries, the 2x2 matrix that you get will always be of this form. And conversely, if you have a 2x2 matrix of this form, remember these polynomials were not completely arbitrary. There were some conditions, but yeah, provided those conditions are satisfied, there exists these sequence of angles phi 0 to phi d such that this equality holds. Okay, and now using qubitization, we can actually implement this desired operation. So let's see how that works. So first thing first, let's recall what happened to the individual eigenstates. So we had e to the I phi 0, z tilde, u of h, da da da, and we have u of h, e to the I phi d, z tilde. And we've shown that if we apply this the energy eigenstate lambda, what we get is basically something very similar, except we, well, okay. So maybe let's just absorb everything into this thing, so into the new phase. So e to the I, let's say theta x tilde e to the I phi 1 tilde z tilde e to the I theta x tilde I phi d tilde z tilde, lots of tildes, lambda s, where cosine theta is equal to lambda. Okay. Now, right. So, okay. So now let's try to use this this fact. Okay. So we know the precise form of this 2x2 matrix. Okay. So, and then what I'm going to do is the following. So I'm going to actually apply the same operator, but not just, but while fixing the state of this ancilla qubit to 0A. The basic thing that I'm trying to do here is this. So like, I want to basically compute this thing. But physically, the thing that what is actually happening is that you first apply the sequence of operators to this initial state. And then what you're gonna get is you're gonna get 0a lambda s, and then p of, let's see, so theta is, let's see, cosine, right? So this would be p of lambda, right? Because here theta is inverse cosine a, and here theta is inverse cosine lambda. So lambda and a, you just identify them. So if you apply the sequence of operation, you're gonna get, first of all, this guy, and then you get some stuff that I will simply not care about. What is important is that it's some, let's say this will be some state on psi, and but on the ancilla qubit, the state will be in 1. Okay. So what we can do now is that we simply measure this extra qubit. And if we measure, let's see, 0, then the post measurement state is p lambda s for any eigenstate. Therefore, more generally, if you begin, let's see. My apologies for not having enough space. Okay. So by linearity, what we can show is that if you have a if you apply this thing to a general linear combination of eigenstates, and then measure A, and if you get 0, then what you're going to get is P of lambda, alpha lambda, lambda s. And that is equal to actually P of h applied to psi, where psi is a general state. And it's the same idea as I told you before. So P of h, what you simply do is that this is simply P of lambda. This is just a definition. And clearly, you just plug that thing in, and you see that this you get the identity. Okay. So this is what I meant by polynomial transformation. So what we started with was that we had a unitary encoding U of h, and then we did this basically a sequence of U of h and single qubit operations, and then we were able to implement P of h probabilistically. Okay. And in that sense, and notice that insofar as we measure the state 0.
What do you mean that you implement this probabilistically?
Right. So if we measure, we measure A, and if we measure 1, then we failed. Then we did not apply P of h. But if we measure 0, then the post-measurement state is P of h applied to arbitrary state psi.
Okay.
Yeah. And in this sense, this is a polynomial transformation. And also in this sense, I don't care too much about precisely what Q of h is. Of course, they cannot be completely arbitrary, but if I only focus on the success case of this measurement outcome, then all that matters is the P of H. Okay. Are there any questions so far? Good. And right. So now we see that we have a very flexible framework to apply some operator to an arbitrary quantum state. Because I missed psi of s. And of course, the downside is that this doesn't always work. If we measure one, then we fail. But at the very least, we can estimate the, let's see, the success probability. At least we can find a condition under which the success probability will be very close to 1. And the thing is, this P of H psi s, it's a subnormalized state, which is exactly the state. So the success probability okay, so before the measurement, the state was P of H psi of S 0A plus some state which is orthogonal to this state. Okay, and therefore the success probability is precisely the norm of this spectrum. So if P of H is unitary, then the success probability would be just 1. Okay, so that's just a fact. And in practice, it turns out that for at least for a Hamiltonian simulation, we can choose P of H so that it becomes very close to being unitary. So at least for a Hamiltonian simulation, we don't even actually need to do this oblivious amplitude amplification. So we just like, we'll just apply qubitization and it will just work with very high probability. And the only question now is how do we actually choose this P of A and Q of A? So clearly we have a goal. So for instance, if we wanted to implement a time evolution operator, we would like P of H to be roughly e to the minus IHT. I mean, roughly because in an ideal world, we would like them to be exactly equal to each other, but clearly this is not a polynomial. So the question is, how well can we actually approximate this function using P of H, given an arbitrary t? And that's the kind of problem that is has been studied very intensively in approximation theory. And I'll tell you more about that soon. But I just wanted to emphasize that again, that the global picture is very simple. If you look at this qubitization, all you're doing is a bunch of single qubit operations interbelieved with a fixed unitary encoding of H. And as you can imagine, these single qubit unitary operators are extremely cheap compared to U of H, because U of H is a like a pretty highly non-local operator. After all, it encodes information about a many-body Hamiltonian. So when it comes down to estimating the cost of the qubitization, things are very simple. So well, you just need one extra qubit. Okay, so there's a caveat. So if you can implement U of H without using any extra resource, then all you need is just one extra qubit, and that's it. And so it's very space efficient. And also to understand the cost of the qubitization, that's also very simple. So remember the number of steps here. So let's say there were like d+1 steps. Okay, let's say there were d steps. Then the polynomial had a degree of I don't know what it was, like d or d-1, but it's yeah, d plus minus some constant. So if you have a low degree polynomial approximation of a function that you want to approximate, then the cost of the qubitization is just the cost of u of h times the degree of the polynomial. So it's really that simple. So this is why qubitization is so nice. It's easy to analyze. It's very clean, and it also doesn't require too many extra qubits. So this is it has so many advantages. But having said that, I should mention that u of h usually requires some extra ancillary qubits. So while the extra ancillary qubit that you need for this z rotations is just one, there are some extra qubit, even more extra qubits that you need for the construction of u of h. But compared to the number of ancillary qubits needed in, let's say, Taylor expansion methods, the requirement is like far more benign. It's very, very modest. Okay, so how does, now coming back to our main question, how does actually Hamiltonian simulation work? Well, okay, so we assume that H is a, well, without loss of generality, we can just expand this e to the minus IHT. I guess I forgot the I here. My apologies. I guess you have that. And this is approximating this function or functions, all sorts of functions by a low degree polynomial is a very well-established subject. So there are like books written about this. And the common method to do this is to use what is known as the Chebyshev polynomial. And this is defined as follows. It's actually the Chebyshev polynomial of the first kind. So here I'm not going to derive anything, but I just want to throw out the definition. It may not be clear why this is a polynomial, but if you think about it, for instance, cosine 2 theta is 2 cosine squared theta minus 1. And, you know, there's a expansion formula. This is so you can like recursively use this formula to basically expand into a polynomial of cosine theta, and that is the Chebyshev polynomial. And there are these approximation schemes for these functions, such as cosine xt and sine xt, in terms of the Bessel functions. So these are the Bessel functions, and these are just the Chebyshev polynomials. And to achieve an epsilon error, it suffices to choose to truncate a polynomial at an order of this form. So you have a term that scales linearly with the absolute value of t as expected. So there's a linear dependence there. And there's a additional additive contribution, which scales like this. So it's essentially log 1 over epsilon. I mean, I guess at short times, this is maybe log 1 over epsilon divided by log 1 over epsilon. But either way, it's a very minor contribution, especially when we're probing the long time regime. Okay, and this was when this first came out. Okay, so result statement of this form was proven in this paper. There was a minor error, which was affixed by these folks. But whatever the case may be, one of the very cool things about the qubitization when it came out was the following. So even before that, I told you about the Taylor expansion method, and there was a certain sense in which these Taylor expansion method was also optimal. So, but it was optimal in a sense that the cost was order big O, like T times let's say polynomial of like log 1 over epsilon. Maybe there was like log 1 over epsilon divided by log 1 over epsilon factor. The details escape me, but it was optimal in a sense that if you try to the dependence on 1 over epsilon when you fix t was optimal up to some logarithmic corrections, and the dependence on t once you fix the epsilon was also optimal because it was nearly linear. And in some sense, this is also optimal in the sense that if you fix one parameter, it's the resulting complexity is optimal in the remaining parameter. But it's actually even, in some sense, like even better than this, because this polylog factor in 1 over epsilon, it's nice, but still it'll scale when epsilon gets very small. Whereas this guy, the coefficient in front of the factor that depends on the time that scales linearly with the time, that's just a constant. So if you go for a very large long time simulation and very high precision simulation, then qubitization wins big time compared to these like LCU based methods. And that's sort of why it works so well in quantum chemistry algorithms. So in quantum chemistry algorithms, you often need a very high precision. So these, even though these log 1 over epsilon, these are, they only scale like logarithmically, it ends up being like not insignificant. So if you multiply, I don't know, like a t by 20 or 30, like that could be a big difference if you compare that to like t times like 5 or something. Okay, so yeah, so qubitization, it's also very practical. It was a nice development.
Yeah, so when you say it works very well for quantum chemistry, I guess this scheme will not be really telling you about the wave function of a, let's say, a big molecule, but it will probably tell you about the energy levels of the molecule. Is that where the advantage?
It's usually these things are always about Hamiltonian simulation. So the problem is you're given a Hamiltonian, microscopic Hamiltonian, and your goal is to simulate e to the minus IHT up to some precision. And you can use all these different methods, but qubitization usually wins in an actual gate cost.
So I guess my question is, in the end, the information you get is the eigenvalue or the energy spectrum, but not the wave function itself.
It depends. So if you use quantum phase estimation, then you will indeed get eigenvalue informations. But when you measure the energy, you collapse into the energy eigenstate of the energy that you measured. So what you would do if you are interested in the ground state problem is that you prepare a sufficiently low energy state and sample the energy spectrum. So you have some, and then you pick the lowest energy state, lowest energy, you guess that as your ground state energy, and you just repeat this experiment many times until you measure that energy again. So yeah, so this way you can create the ground state.
I see. Okay, so you can also measure the ground state wave function, so to speak.
Right, yeah, but of course you have to have a non-zero overlap in your initial state.
Yeah. Okay.
Yeah. Okay. Good. So yeah. So I guess yeah, in these, so yeah, so here, yeah, okay, that's all good, but there's like one little thing that you might be worried about, which is that was the success probability. Just to be clear, the polynomial approximation of e to the minus IHT that these guys considered is really it's really a polynomial that satisfies all the conditions. So this p, we have this p and q such that p squared plus 1 minus a squared q squared must be equal to 1. And there are some conditions in the degree. So you can see that p, the norm, it cannot be too large. So if you approximate this e to the minus IHT by some like a polynomial that can potentially have a very large norm, then that's no good because then this condition will not be satisfied. And indeed, the polynomial that these guys developed, they are indeed polynomials which are properly normalized. So this condition can be satisfied. Okay. Yeah. All right. So the remaining questions at this point is how do we actually implement the unitary encoding, unitary oracle? So I mean, what I mean by that is the unitary encoding of age. And the related question is, are there any examples? So I was a bit of abstract today. So, you know, are there any examples that, and we're going to discuss that the next time. So the next time we're going to focus on how to actually construct these unitary encodings. Okay, so that's ends a little early, but I guess I can take questions.
So Oracle is just another name for unitary encoding that you showed?
Yeah, so yeah, just I think I should have just written as unitary encoding of age.
Okay. Yeah, it looks like there are a lot of students in the audience. Most of them seem to be students by now. And I'm curious to know how well the students are taking in these lectures. So any comments would be very welcome. Just leave a like a short one sentence note in the chat room as to how you
Yeah.
feel, you know.
Yeah, if there's a, if you think it's too slow or fast, it'll be good to know actually.
I mean, for me, the pacing is just perfect. But maybe for the students, I don't know. I think I think this is a good time to express your thoughts or wishes.
Yeah. Maybe like a confidential.
Yeah. That's good too.
Yeah.
Okay, well, if not, I personally think that today's lecture was really an. Oh, there's a question.
Oh, okay. So, oh yeah, but if you have any questions, I'll be happy to always answer. So, yeah.
Yeah.
Yeah, it's good to ask questions because I know that sometimes it's kind of weird to. It might be easier to like ask questions in the chat room. Actually, I found that that's sometimes easier.
Yeah, I'm pretty sure that with the exception of Professor Kim, everyone here is new to quantum computing. None of us has ever written a paper on quantum computing. So being naive is the norm here.
Yeah.
May I ask where you are? Are you a student, Mr. Ko?
Hi, good morning.
Yes.
Hello.
Okay, all right. I'm not a student. I'm actually teaching. But I do my research in nuclear physics.
Oh,
Yeah, so that's why I say I'm very new because I have just tested with Qiskit just a few weeks, maybe 1 week ago. Yeah,
but
so
you're a
so
professional, right?
yeah, yes.
Okay, so the math cannot be too hard for you.
No, the math is not too much, but I need to reorganize the various information, why we need this operator and that.
Okay. So question from Mr. Han. Can,
Yeah.
First of all, Han Jongyun, who are you? Are you a student?
Let's see. I guess maybe I can answer the question first.
Yeah.
Yeah. So the answer is no. You cannot implement Qubitization to the bosonic Hamiltonian, and the reason is that the bosonic simple harmonic oscillator is not a bounded operator. So this is the Hamiltonian, and the spectrum is was it? Well, sorry, it's been a while. Forgive me, but I forgot the lowest energy, but it goes all the way to infinity. So unless you somehow truncate the Hilbert space to a smaller Hilbert space, you cannot encode this H into a unitary.
Mm. Good. So yeah, that was a good question. Yeah. Any other questions?
Can I have a very naive question?
Sure.
Yeah, since I'm actually looking to implement quantum computing for nuclear theory in a Hartree form, which is similar to what they did for chemistry. So, what do you suggest is the best way for me to start? Because I am looking at the Qiskit at the moment. So, should we learn how to solve quantum mechanics, for 1D problem first, or should we jump immediately into solving some more advanced things? Which is the best way?
Sorry, like, did you say like how to solve Hartree fuck on a quantum
Yeah,
computer?
yeah.
Let's see. Okay, so it's not something that I have very actively followed, but I vaguely remember Google group like showing how to do that on their processor, and then there was a theory follow-up which showed that there are some difficulties to solve Hartree fog on a quantum computer. I mean, if you use a particular approach. So yeah, but am I talking about something that is related to what you're saying? But I just wanted to, yeah, I'm not done with my answers, but I just wanted to be sure we're on the same page.
Yeah. Yes.
Oh, okay. So that suggests to me that maybe it's maybe it's better to maybe if the goal is to solve Hartree fuck, maybe it's better to use the classical computers because they're already very good. So I think the quantum computers, they're like supposed to be better at solving more correlated systems, and yeah, these are algorithms like quantum phase estimation. They are that's precisely the goal. It's more general and it's more resource intensive, but it's more general and in particular applicable to correlated systems.
Okay, thank you for the answer.
Okay. Any further questions? Yeah, I tried to read through this original paper on qubitization by Chuang, and it was a very, very dense paper, 4-page PRL. So it was intimidating, but after listening to today's lecture, I feel like this is rather easy. I mean, thanks to the
Yeah,
methodology of
yeah. I mean, there are some details. For instance, I didn't tell you how to prove the converse, so that's a non-trivial thing. And also, you need to. There's also this problem, right? So let's say I have a polynomial. So here I indeed I have these polynomials. But given these polynomials, even though we know that there is a set of angles, we should still be able to find these angles, right? If that process is not easy, then this is not going to be very good. And there are indeed such methods to do that. So these are all like different facets of qubitization that people worked out, but I haven't covered those.
Okay. Okay, so clearly there will be more to come next Wednesday at 10 a.m. And I hope to see you all back. Let's share thanks to Professor Kim for giving very, very nice and inspiring lectures today. Thank you.
Okay, thank you.